Today we're going to begin looking at 8.4 vector and parametric equations of a plane. So there's 4 different ways that a plane can be determined. So first way is by a line and a point not on the line. Our second is 3 non-collinear points. These are 3 points that are not on the line, and 2 intersecting lines, and 2 parallel and non-coincident lines. So we can give you a visual of this where we use parallelograms to represent a small part of the plane designated by pi. So where we have our line, so that's our line, and we have our point, so say our point's over here. Then we have our second example here where you have 3 non-collinear points, and then you have 2 intersecting lines, and then you have your 2 lines that are parallel and non-coincident. And any one of these conditions can form a plane. So looking a little bit further at vector and parametric equations of a plane in R3. In R3, a plane can be determined by the vector r subscript 0, which is equal to x, y, z, where our x, y, z there is a point on the plane, and 2 non-collinear vectors are vector A and B. Basically, what you need is 2 direction vectors and a point to find a vector equation of a plane. Any pair of non-collinear vectors are coplanar and can be used. So our vector equation of a plane here is kind of hard to see here, so I'm going to rewrite it to our right-hand side here, where we have our vector r is equal to our vector r subscript 0, where this is our point, plus s times our vector a plus t times our vector b, where a and b here are 2 direction vectors. Similarly, you can look at this using parametric equations of the plane, so our x, y, and z. So now we will begin looking at our first example. Our first example, we want to determine the equation of the plane given our 2 vectors a and b. So we have our vector a here and our vector b. Now, we know that we're going to go from our one point to our other point, so we want to find what that vector is. So since we know a and b, we're able to find our p naught p, okay, which is going to just be 1, 4, 0. Or we can do a scalar of that and multiply it by -2 times our 1, 4, 0, which will give us -2, -8, 0. So therefore, since we want to determine the equation of the plane, we know that our equation is just equal to our vector r, which is equal to r subscript 0 plus s times our vector a plus t times our vector b. Sub in our known, so we're going to take our point, -2, 8, 0, plus our s times our vector a, so 1, 2, -1, plus t times our vector b, which is 0, 2, 1. And that is our equation. So now let's go ahead and look at example 2. So now we can look at our example 2. We want to determine a vector equation and the corresponding parametric equations for the plane that contains the points A, B, and C. So what we need to do first, so our first step is to do our direction vectors. So what we're going to do is we're going to find AB. So when we do that, AB is going to be equal to 0, -2, and -8. And then we're going to look at BC, which is going to be equal to 5, 0, 1. So therefore, we are going to have our vector A. We're going to actually factor out that scalar of negative 2. And what we're going to be left with is 0, 1, 4. And our BC was 5, 0, 1, so our vector B here is going to be 5, 0, 1. So therefore what we're going to do is we're going to take our point A, and that's going to be our point, and then our vector A and B are as you can see. So we have our vector equation equal to negative 1, 3, 8 plus S times 0, 1, 4 plus T times 5, 0, 1. And now in the second part here, we want to determine the corresponding parametric equations. So therefore we have x is equal to, take our x, so negative 1, plus our 0, so plus 0s, and then plus 5t. And then we have y is equal to 3 plus s, and the t times 0 is just going to be 0, and then we have z is equal to 8 plus 4s plus t. We can rewrite our x as negative 1 plus 5t. So those are our parametric equations. Now in part B of our equation here, our example, we want to see, do either of the points P or Q lie on this plane? So we know our parametric equations from part A here. So what we're going to do is we're going to say our 14, since that is our point X in both P and Q, is equal to negative 1 plus 5t. So that, just recall, comes from our parametric equation from above. So therefore 15 is equal to 5t, and therefore t is just going to be equal to 3. So since we know that t is equal to 3, we're going to use that in our parametric equation here. We're going to first find s from our parametric equation. We're going to know, since that both our y's are both 1s in both p and q, we have 1 is equal to 3 plus s. So therefore s is going to be equal to negative 2. So now what we're going to do, we're going to use our parametric equation for z and figure out, well, which one of these, or do either of them, lie on the plane. So we know z is equal to 8 plus 4s plus t. So let's sub in our found values. So 4 times negative 2 plus 3. So we have 8 minus 8 plus 3, so we get this equal to 3. So therefore you see 3 is part of P, so therefore P is on the plane and Q isn't. Now in example 3, you're going to need to rewrite the plane here. Just some errors with the equation. So a plane has our vector r is equal to 6, negative 2, negative 3, plus s times our vector a, which is 1, 3, 0, plus t times our vector b, which is 2, 2, negative 1, where s and t are elements of the real numbers as its equation. So we want to determine the point of intersection between our pi and our z-axes. So our first step here is going to be to rewrite in parametric form. So I'm going to rewrite this so that I have x equals 6 plus s plus 2t, y is equal to negative 2 plus 3s plus 2t, and z is going to be equal to negative 3 minus t. All right, second step, z-axis we know is going to be 0, 0, and we're just going to hold that as c. Third step, we're going to take our above and solve for our, we're going to use 0, okay, for our x and our y, okay, since we know our z-axis, that x and y are both 0. So 0 is equal to 6 plus s plus 2t, which is equal to negative 2 plus 3s plus 2t. Now, just like linear systems, we're just going to subtract these, get rid of one of our variables. So we're going to subtract them, so the t's are going to actually be gone. 6 minus negative 2 is going to give us 8. And s minus 3, so that's 1 minus 3 is going to give us negative 2s. This is equal to 0. And now we're going to solve, and s will be equal to 4. Now our fourth step here is, since we know what s is going to be equal to, we're going to sub into our x, our parametric form of our x. So we have 0 is equal to 6 plus 4 plus 2t. And the reason we're doing that is so that we can solve for our t. So we have negative 10 is equal to 2t, so therefore t is going to be equal to negative 5. And then in number 5 here, we have z is equal to negative 3 minus negative 5. Remember, those two negatives will make a positive, so therefore z is 2. So therefore, the point of intersection is at 0, 0, 2. Now, in example 4, we want to determine the vector and parametric equations of the plane containing our point P and the line. We're going to have to rewrite our line here, where r is equal to 1, 1, 1 plus s times negative 1, 1, 0. So here you notice that we have a line and a point. Okay, so our line gives us our point 1, 1, 1 plus our direction vector, which is a. So we have our point, which is 1, 1, 1, and we have our direction vector, which is our a, negative 1, 1, 0. So visually, if we're thinking about our plane here, we have our line and we have a point. All right, so those can connect there. So therefore, we're going to call that A, right, our point A on our line. So AP is going to be equal to 0, negative 6, 8. So therefore, if I factor out a negative 2 from this, we're going to get that our vector B is going to be equal to 0, 3, negative 4. Okay, that comes from working with our point P here, right? So our point P and our point 1, 1, 1. So we have our vector B, so therefore we want to determine the vector and parametric equation. So the vector equation is just 1, 1, 1 plus s times negative 1, 1, 0 plus t multiplied by our vector b, 0, 3, negative 4. And therefore our parametric equations are just 1 minus s, y is equal to 1 plus s plus 3t, and z is equal to 1 minus 4t. And now in our last example here, we want to determine the vector equation of the plane containing the following two lines. So looking here, we have our two lines where we have our resultant equal to 4, negative 3, 5, plus s times 2, 0, negative 3, and our line 2 where our vector r is equal to 4, negative 3, 5, plus our t times 5, negative 1, 1, negative 1. And remember, we want to determine a vector equation and of the plane containing those two lines. So here we know that our A is equal to 2, 0, negative 3, and we know that our vector B is equal to 5, 1, negative 1. And we know that we have our point equal to 4, negative 3, 5. So since we know all three of those and we want to determine the vector equation, all we need is our point, our vector A, and our vector B. So therefore, our equation, our vector equation, is just equal to 4, negative 3, 5, plus s times our 2, 0, negative 3, so that's our vector A, plus t times 5, 1, negative 1. And that's all that needs to be done there. So that's when you have your two lines that are intersecting one another. And that is the lesson for today.